Welcome. Today we're covering the Chapter 8 review questions from Berean Builders Discovering Design with Physics. As usual, I'm not going to go through the definition terms because those are pretty easy to find in the book. But let's start with question 2. A person does 100.0 joules of work on an object. How did the object's total energy change? How did the person's total energy change? So the person is doing the work on the object, and so when that happens, that object is going to increase in energy. So the object's total energy is going to increase by 100.0 joules. And then the next part is asking about the person. Well, the thing doing the work is going to lose that energy. So the person's total energy is going to decrease by 100.0 joules. So the key thing is when work is done on something, it gains energy, but when it is done by something, it loses energy. So now for question 3, someone pulls a load horizontally using a rope tied around the load. How does the work being done when the person pulls the rope at an angle of 45 degrees relative to the horizontal compare to when it is pulled at an angle of 15 degrees relative to the horizontal? The magnitude of the force is the same in both cases. So I'm just going to draw a little, and this is not really part of the answer, but I'm going to draw a little diagram to demonstrate what is going on, okay? So here we have this box and it's being pulled horizontally, and the angle here is 45 degrees, okay? And we're going to call this force F, and that the force is going at that 45 degree angle, okay? Then the second load is being pulled at a lower angle. If we draw that horizontal, it looks kind of like that. Okay, and that angle is 15 degrees. Okay, but it's still the same force F. Okay. The work that is being done is going to be parallel to the direction that the object is ultimately moving, which is going to be horizontally, right? And so there is less force actually happening on the horizontal than there is on this diagonal in both of these cases. But it's going to be much less on this 45 degree versus the 15 degree angle. Okay, so the work is greater when the angle is 15 degrees. If the force is the same, then the only thing different is the parallel component, right, which is that horizontal. And the larger the parallel component of the force relative to the displacement, the more work is done. And so since 15 degrees is closer to the parallel with the horizontal than 45 degrees is, there is more parallel component and thus more work at 15 degrees. So that's a really long explanation. The answer doesn't need to be that long, but just wanted to describe why the answer is what it is, that the 15 degrees has more work that is happening there. Question 4. A diver stands at the edge of a diving board and takes a step off, falling into the water below. When is the diver's potential energy the greatest, and when is the diver's kinetic energy the greatest? So the potential energy is greatest while that diver is standing on the diving board. And the kinetic energy is greatest at the instant he hits the water. Potential energy depends on the mass and the height. And the mass doesn't change, but he will never be higher than when he is standing on the board. And so that is where the maximum potential energy is. When he falls, that potential energy is going to be converted into kinetic energy. And so then once that height is 0, that means all of that potential energy has been converted. And that is, of course, at the instant that he hits the water. And so that's the point that the kinetic energy is the highest, because all of the potential energy has been converted to kinetic. For question 5, an object has a potential energy of 154 joules when it is at a height of 24.5 centimeters. What is its mass? So let's kind of write out what we have. We've been given potential energy, which is 154 joules. We have height, which is 24.5 centimeters. And we know at this point that we're going to need to convert that to meters, so we'll just go ahead and do that. 0.245 meters. Okay. And so we essentially have 2 of the 3 things that we need to have a full potential energy equation. So potential energy equation, potential energy equals, we have the mass times gravity times height, okay? And what we're asked to determine is mass, okay? So we have potential energy, we have height, we know gravity, and we need to determine mass. So let's first, I like to get my variables isolated before I do all the calculations. So I'm going to get mass by itself here. And so that's just going to be mass equals potential energy divided by gravity times height. Okay, and so working that out, we'll get 154 joules divided by 9.81 meters per second squared times 0.245 meters. And just looking at our units here, remember that joules equals kilograms times meters squared over seconds squared. It's essentially newtons, but we've added an extra meters at the top. Okay. And so on the bottom, we are dividing by meters squared. There's 2 meters and seconds squared. And so we're going to be left with kilograms. Okay. And when we fully calculate all of this out, we'll get 64.1 kilograms. And so our answer here is the mass is 64.1 kilograms. For question 6, a car has a kinetic energy of 11,000 joules while traveling at 2.5 meters per second. What is its mass? So we're given kinetic energy, 11,000 joules. We have our velocity of 2.5 meters per second, and we need to determine the mass. So for this, let's use our kinetic energy equation. Kinetic energy equals 1/2 of the mass times velocity squared. And we are given kinetic energy and velocity. We need to determine the mass. So once again, I'm going to isolate this mass variable before I solve. And so with that, I'll get mass equals 2 times the kinetic energy divided by velocity squared. I'm plugging in all of those numbers. 2 times 11,000. Oh, why did I put a squared there? 11,000 joules divided by our velocity, 2.5 meters per second, and all of that squared. So just like before, I'm going to have meters squared per second squared that I'm dividing by on the bottom, and that's going to leave kilograms up at the top because joules is kilograms times meters squared per second squared. When I calculate this out, I'm going to have two significant figures because both of these are actually two significant figures here. And so that is going to round to 3,500 kilograms. So the mass is 3,500 kilograms. For question 7, a roller coaster starts from rest at a hill that is 65.8 meters high. It rolls to the bottom and then rises to the top of another hill that is 16.4 meters high. Ignoring friction, what is its speed at the top of the second hill? Okay, so I have an initial velocity. We're just going to go in order writing these out. So starts from rest. That is the information here. So the initial velocity equals 0 meters per second. Then the hill is 65.8 meters high, h, and I'm going to call this h1 because I remember that there's going to be another height that I'm given in a minute. 65.8 meters. It rolls to the bottom and then rises to the top of another hill. That is my height 2 is 16.4 meters. And we're ignoring friction and wondering what the speed is at the top of the second hill. So we're going to put together two of our total energy equations, and the total energy is going to be the same whether we're at the top of the hill or we're at the top of the second hill. So we'll be able to then make them equal to each other and solve for what we're missing. Okay, so let's look at total energy at these two different spots. So what is the total energy when we are at the top of the hill based on the information that we had? So total energy, we're going to say initial, we'll call this, okay, it's going to equal the kinetic energy plus the potential energy plus, well, that's it for this because we're ignoring friction. So kinetic energy plus potential energy. So our kinetic energy is 1/2 mass times velocity squared, and our potential energy is mass times gravity times height, right? So at the top of this hill, our initial velocity is 0. So our kinetic energy is 0. For our potential energy, we weren't given mass, so we're going to have to just leave that as an m. And multiplying that times gravity. And our height, 65.8 meters. And that is going to give us, we still have mass times 645 meters squared per second squared, having that as 3 significant figures for that. So that is our initial. We still have an unknown variable, but we're gonna just keep going. So at our second hill, we're going to do the same thing. Our total energy equals kinetic energy plus potential energy. And so I'm just going to refer back to this instead of rewriting it. So our kinetic energy, this time we are moving, right? And we don't know how fast. 1/2, we don't have the mass, and we don't know the velocity, but it is definitely moving at this point. And then we also do have potential energy because there is a height involved here, 16.4 meters. So for the potential energy, we have mass times our gravity, 9.81 meters per second squared, and our height is 16.4 meters. And so we just can't simplify the kinetic energy any further, but for the potential energy, we have mass times 161 meters squared per second squared. Okay. And so like I said before, we know that the total energy, whether we are at the top of the first hill or the top of the second hill, is the same in each case. And so what we're going to do is we're going to set these as equal to each other, this part and this part. So our mass times 645 meters squared per second squared is equal to 1/2 mass times velocity squared plus mass times 161 meters squared per second squared. Okay, now this is where we can finally get rid of this mass because it is part of every single piece of this equation. It just cancels out. That's because it's part of every single expression within there. And so now all we're left with is velocity as an unknown variable, and we can solve for that. So first we're going to subtract 161 meters squared per second squared. And we'll get 484 meters squared per second squared equals 1/2 velocity squared. Going to multiply both sides by 2. Get 968 meters squared per second squared equals velocity squared. And now we'll take the square root. And with that, we'll get 31.1 meters per second equals the velocity. Now, the question isn't asking us about velocity, or we would have to give some kind of direction. It just says speed, so we're going to answer it as speed. So the speed is 31.1 meters per second. For question 8, a bicyclist pedals her bike to a speed of 6.75 meters per second. She then stops pedaling and starts to ride up a steep incline. How far will her bike climb before it stops? If she just lets the bike go, how fast will she be traveling when it rolls back to the bottom of the incline? And we can ignore friction. So just graphically, what is happening here is she is going up this hill, and then the second question there has her going back down it, back down the same hill. She's not adding any more work, any more force to the bike. She's just coasting up to the top of the hill. And so we're wondering how far up that hill she's going to get before she stops, since she's not adding any acceleration there. So our initial velocity equals 6.75 meters per second, and we want to know what's the height. So let's use our total energy equation. Total energy equals kinetic energy plus potential energy. Okay, and so that kinetic energy is going to be 1/2 times the mass, which we don't know, times that velocity squared, 6.75 meters per second squared. And the potential energy She's starting at the bottom of this hill, so there is no height to it. And so since our potential energy equation has height as a part of it, that's going to be 0 because we're multiplying it all times 0. When we calculate this out, we'll get 22.8 meters squared per second squared. And this is actually times mass. I should have put that at the beginning, but times that mass. Okay. So this is at the bottom. So now let's do what that total energy is at the top. Total energy equals kinetic energy plus potential energy. So our kinetic energy at the top is going to be 0 because our question is asking how far will it climb before it stops. So at the top of however far she can go, it may not necessarily be to the top of a hill, but just as far as she can go, that velocity is going to be 0. So we could even write here velocity final equals 0. Okay, but that of course is going to make the kinetic energy 0. And then our potential energy is going to be, of course, mass times gravity, 9.81 meters per second squared, times our unknown height. That's what we are asking for. So now we can make these two equal to each other. I'm just rewriting each of these into a new equation. Okay, just like before, we can cancel out mass because it's part of both expressions there. Then we'll divide both sides by 9.81 meters per second squared. Trying to isolate this height here. And we'll get 2.32 meters equals the height. And so our final answer is that she will reach a height of 2.32 meters. Now, we are not done. There is a second part of the question. If she just lets the bike go, so like once she gets as far as she can go, and she just lets the bike go, how fast will she be traveling when it rolls back to the bottom of the incline? And this is just taking into account things that we have already learned. And so she gets up here. When she gets back down to the point that she started, the only force that was being put in here was the acceleration due to gravity, right? And that same force is being applied when it goes back down the hill, just in the opposite direction as far as the velocity is concerned, right? So it's changing the sign. So the speed at which she's going when she gets to the bottom of the hill is actually going to be the exact same speed as when she started. She's gaining all of that back based on the acceleration due to gravity. So she'll be traveling at a speed of 6.75 meters per second at the bottom of the hill. For question 9, when friction works on an object, what happens to the sum of the object's potential and kinetic energy? What happens to the temperature of the object and its surroundings? So for this one, the sum of that potential energy and kinetic energy is going to go down, and the temperature is going to go up. So, and the reason for this is that we know that friction converts kinetic energy into heat. So the sum of the potential energy and kinetic energy goes down. And of course, the heat is going to warm the object and its surroundings. For question 10, someone pushes on a 2.5 kilogram block horizontally, doing 150.0 joules of work on it. What will its initial velocity be? And if the coefficients of friction are 0.441 and 0.298, how far will it slide before it comes to rest, assuming the floor continues to be horizontal the entire time? So let's write out what we have. We have mass, 2.5 kilograms. We were given kinetic energy, this work that's being done on it, which is 150.0 joules. We don't know what the initial velocity is going to be. We're given coefficients of friction, so we have mu s equals 0.441 and mu k equals 0.298. So let's do what we have done before. So initially, we have our kinetic energy is going to be, of course, 1/2 mass times velocity squared. And we were given this kinetic energy, and we have the mass, and we don't know the velocity, right? So let's go ahead and isolate the velocity here. So velocity is going to equal 2 times our kinetic energy divided by mass, and of course a square root of all of that. And so we'll get 2 times 150.0 joules divided by 2.5 kilograms, and we're taking the square root. So as far as units go, just remember that joules is the same as kilograms times meters squared over seconds squared. Okay, and so kilograms is going to cancel. We're left with meters squared per second squared, and when we take the square root, we're going to have meters per second, which is velocity. And we have to go to just 2 significant figures with this, so we're going to get 11 meters per second as the velocity. So the first part of this question is that the initial velocity will be 11 meters per second. Now, this question actually does ask for velocity. Usually from this book in this section, they're asking about speed because we're not worried so much about the direction. But because this asked about velocity, technically we should be giving a direction. Now, we don't have any directions. We don't have east, west, right, left on here. But what you can say to give the direction is just say, in the direction of the push. And that covers us for that. Now, the next part of this question is asking, based on the coefficients of friction, how far will it slide before it comes to rest? So it's been given one big push. There's no extra work being added to it. And how far is it going to slide based on what it's going to lose to friction? So we're going to do another total energy equation, but this time we're going to have friction in it. And so that's going to be total energy is kinetic energy plus potential energy plus the work from friction. Okay. So our total energy, this is our initial, and I could have written this one with total energy equals kinetic energy plus potential energy plus work from friction also, but the potential energy would have been 0 because we are on the floor, and the friction would have also been 0 because this is the initial push before we're allowing friction to come into play. And so the work from friction would be 0 in this initial also. So I just kind of shortened it and said the only part that's going into this initial energy is the kinetic energy. And that total energy is 150 joules. So our total energy is 150.0 joules. So that's going to equal our kinetic energy. Well, our kinetic energy in this case is going to be 0 because we are going to the point where it has come to rest. Okay, so again, we could say velocity final from here equals 0. Our potential energy is also still 0 because we are on the floor. And so all that we are taking into account here, the only work that's being done on this, or that has been done on this box from the time it was pushed until it goes to rest, is the work from friction. So this work from friction is going to be defined as our force of friction. So our mu times our mass times gravity, that's our force from friction, times our delta x, our distance traveled. So our mu that we're going to use, because this box was moving, we're going to use the kinetic coefficient of coefficient of friction. So 0.298 times our mass, 2.5 kilograms, times 9.81 meters per second squared, times our unknown delta x. Okay, and so we're going to get 150.0 joules. And instead of multiplying all of this out now, I'm just going to go ahead and divide the 150 joules divided by all of this, because this doesn't matter, right? And so all we have here is all of this times delta x. And so this is just going to give us all our answer in one neat movement. So divided by 0.298 times 2.5 kilograms times 9.81 meters per second squared. And that is going to give us one significant figure, because we have this 2.5 kilograms, or sorry, two significant figures is what I meant to say, because we have 2.5 kilograms. We're going to get 21 meters. That equals our delta x. So the rest of our final answer is that it will slide 21 meters before coming to rest. Question 11, a 817-gram block slides down a ramp starting from rest at a height of 2.16 meters. It reaches the bottom after sliding for 5.22 meters and has a speed of 4.98 meters per second. What frictional force did the block experience? So here we have mass equals 817 grams. We're going to go ahead and convert that to kilograms. starting from rest, so our initial velocity equals 0. We have height equals 2.16 meters. Reaches the bottom after sliding for 5.22 meters. So that's our delta x. And our velocity final, when we reach that bottom, is 4.98 meters per second. So let's go ahead and get our total energy initially and at the bottom of this ramp. So initial, total energy, kinetic energy plus potential energy plus, we'll go ahead and throw this work from friction there. So our kinetic energy is going to be 0. We're starting at rest, so that velocity is 0. Our potential energy is our mass, 0.817 kilograms, times gravity, 9.81 meters per second squared, times our height, 2.16 meters. And then our work due to friction, we're not moving yet, so that is 0. And so all of that calculated out to 3 significant figures is 17.3 joules. Okay, so we have meters per second squared times meters, so meters squared per second squared, kilograms equals joules. At the bottom, so at the bottom, our kinetic energy, we are moving. So we'll take 1/2 of our mass and our velocity is 4.98 meters per second. We will square that. Plus, now our potential energy is 0 because we're at the bottom. And our work due to friction is what we're trying to figure out. And so we calculate that out to 3 significant figures. We get 10.1 joules from all of the kinetic energy plus that work due to friction. So now we can set these equal to each other. And so we have 17.3 joules equals 10.1 joules plus work due to friction. And so our work due to friction is going to be 7.2 joules. But that is not quite what this is asking for. We're asking for the force from the friction, not the work. So remember that work includes the aspect of our delta x, right? So our work due to friction equals our force times delta x. And so that means 7.2 joules equals our force times our delta x was 5.22 meters. And so we'll divide both sides by 5.22 meters. And I'm running out of room here, but our frictional force then is going to be 1.4 newtons. And so my final answer frictional force was 1.4 newtons. So make sure that you're paying attention to exactly what it's asking for. We couldn't stop with just the work of friction on this one. Question 12 asks us if the block in this previous question 11 took 1.67 seconds to slide down the incline, what power did friction exert? So we're given some extra information. Our delta T, 1.67 seconds. And we know that from that previous problem, our delta WF equals 7.2 joules. And this is all from our power equation. Just power equals our delta W divided by delta T. Okay? And so all we got to do is plug these in. 7.2 joules divided by 1.67 seconds. And we get 4.3 joules per second. And joules per second equals watts. So our actual answer is 4.3 watts. For question 13, a crane lifts a 3,125 kilogram load straight up in the air at a constant velocity. If the crane uses 1,632 watts, how long will it take for the load to reach a height of 24.5 meters? So our givens here is mass, 3,125 kilograms. Our velocity equals constant. Our power is 1,632 watts. So you just have to know that watts is a power unit. Our delta X, how far we're going to move this object, equals 24.5 meters. Okay, so we have power equals delta W divided by delta T. So this work is going to be the force that is parallel to the displacement times the actual displacement. And so that's going to equal our mass times gravity for the force times our delta X. So our mass is 3,125 kilograms, 9.81 meters per second squared, times 24.5 meters. So we're going to go ahead and rearrange this equation and then just plug this whole thing in here. And we're solving for delta T, so our delta T equals our delta W divided by our power. So we'll just plug all this in here, 3,125 kilograms times 9.81 meters per second squared times 24.5 meters. All of that divided by our power, 1,632 watts. Okay, and so remember our power is joules per second, right? And here we have kilograms times meters per second squared times meters, which is the same thing as joules. And so joules divided by joules per second is going to give us seconds as our unit. So calculating all of this out, we're going to get 460 when we are rounding to three significant figures. But of course, if we write it this way, it is not three significant figures. And so we have to rewrite this as 4.60 times 10 to the second power. And this is seconds. And so our final answer here is that it will take 4.60 times 10 to the second For question 14, which of the following is an energy unit? Newton, watt, kilowatt hour, or meters per second squared. So kilowatt hour is our energy unit. Newtons, of course, are force. Watts are power. And meters per second squared is acceleration. And since power is energy divided by time, a kilowatt hour is energy divided by time times time, which is energy. And so this is the typical unit that is used to bill you for electricity. Question 15. The lights in your house suddenly dim and stay dim for a while. However, when you turn off the oven, the lights go back to normal. What explains this kind of situation? So what's happening when this happens in your house is that all of the appliances in your home were requiring more power than what could be supplied to it. And so turning off the oven reduced the power that your home needs so the lights can burn brighter, since more of the available power can go to them. So when appliances require more power than what they can get, they either stop working or they don't do their job as well. And so in the case of lights, that means that they become dim. And so by shutting off the oven, more power went to the lights, which allowed them to work more like they are supposed to. So that is the end of these review questions. If you have any questions, feel free to post them in the comments.